In this lesson, we will explore the concept of inverse functions and apply properties of inverse functions to solve problems. So before we start, we want to look at what is an inverse. The inverse of a relation or a function is the reverse of the original relation or the function. So let's bring us back to the machine concept. X would be our input that is put into the function f of x to receive the output, which in this case are lemons. We would take those lemons and put it in the inverse function, which is the machine, to result in our input, our original apples. So the notation that we use when we're talking about inverse is f inverse. So if you notice, it kind of looks familiar. It looks like f to the power of -1, but it is not that. F inverse is the name of the inverse relation or function. This is not the same as the reciprocal or the relation function raised to the power of -1. It is just the notation used to represent the inverse of our original function. F inverse of x represents the expression for calculating F inverse. And that's really, really critical. I don't want you mixing those up. Okay, that just is the notation used for the inverse. Okay, so the inverse of a function can be obtained in three different ways. The first way would be if the function is represented by a set of ordered pairs or a table of values, all we do is interchange them, which fancy word for switch. All our x values in our original function f at x becomes the y values for f inverse of x. Likewise, y values for my initial function f at x becomes the x values for the f inverse of x. If the function is represented by a graph, we're just reflecting the graph along the line y equals x. The third way is if the function is represented by an equation, we can interchange the x and y values and then solve for y. And we will be exploring all three of these ways. Starting with the first, let's determine the inverse of the function defined by the following. So our f function includes the following ordered pairs: 2 and 1, 5, 3, 3, 1, 4, 2. So if we wanted to determine the inverse, we would interchange the x and the y values. So the inverse function, so f inverse would be 1 and 2. You interchange the x and the y values. The second ordered pair would become 3 and 5, 1 and 3, 2 and 4. Okay, if we recall right from the very first lesson that we did in this unit, is the inverse of function. Now, in order to decide whether that is the case, we look and observe our x values. If they don't repeat, we can say that the inverse is a function. However, in our case, that's not the case. We have two values of x that have two different y values. So therefore, we can say, therefore, the inverse, and then notation again is f inverse, is not a function since each x value does not have a unique y value. Because remember, by definition, each value of the domain has a unique value of the range. In this case, that's not the case. X repeats itself, so therefore this is not a function. So in B, we're given a table of values. Again, in order to determine the inverse, so if this was f at x, the inverse would be, the inverse of x would be interchanging those x and y values. So x and y in this case would be 2 and 1, 4 and 2, 6 and 3, 8 and 4. Right? Is the inverse a function? What we observe there, each x value is unique. It hasn't been repeated. So therefore we can say, therefore, the inverse is a function each value of x has a unique y value. Excellent. Okay, so that's the first way. When we're given a function represented as ordered pairs or a table of values, we simply interchange the x and the y values. The second way that an inverse can be represented is reflecting the graph along the y equals x. Now, taking out our ruler, y equals x again, I'm going to just draw it as a dotted line, would be like such. Okay, let's just, if we reflect, that means our graph would, the graph of the original function and its inverse would be reflected about this line. Now, the quickest and easiest way to just show that is by taking each of these coordinates, so -2 and 4, okay, -1 and 1, 0, 0, 1, 1, 2, and 4. And if we interchange those values, we will see that the original and its inverse, and our original here is our quadratic function, okay? So, and at its inverse, we would take those coordinates and interchange them. So -2 and 4 on my original function, on its inverse, that would be interchange. So 4 and -2. So if we go to 4 and -2, that would be 1 point on the inverse. -1 and 1, switch those. X is 1, y is -1. Okay, 0 and 0. Okay, that doesn't change. So that's called an invariant point. So that's just a side note. A point that does not change from the original to the inverse is called an invariant point. So 0, 0 does not move from the original to the inverse. Now 1 and 1 also remains the same. So that's another invariant point. And we have 4 and 2, 4 and 2. So 2 and 4 originally. So 2 and, so then we would draw the inverse. Remember that notation of inverse of x. Now, is the inverse a function? Well, we know because we do have the graph, we can apply the vertical line test. If we apply the vertical line test, let's show that ruler, just to remind ourselves of that. We take a vertical line and we, if you notice, the vertical line would be intersected by the graph at more than one point. That tells me it fails the vertical line test, and this inverse is not a function. So therefore, the inverse is not a function since it fails the vertical line test. I wanted to show how our original function and our inverse are reflected about the line y equals x. If you notice, I showed those arrows that they're the equal distance to y equals x. This is right on there. This is right on there. But if you see this point here, 1 and -1, and 1, sorry, -1, 1, and 1 and -1 is equal distance to that line y equals x. And again, we use the ordered pairs. So the original function, which is f at x, I'm just going to show that table of values. Okay, from left to right, we said -2 and 4, -1 and 1, 0, 0, 1, 1, 2, and 4. And the inverse coordinates, again, we just interchange them. And that is exactly what's happening when you're determining the inverse based on our original function. So 0, 0, 1, and 1, and 4, and 2. Okay, moving on. The third way we can decide or to obtain the inverse is algebraically. So given the equation of the following function, determine algebraically their respective inverse and state whether the inverse is a function. So I'm going to just take it step by step. We have f of x is equal to negative 4x plus x. So we can identify that as a linear function. Now, when we are determining the inverse, we need to make sure that we follow certain steps. The first thing we want to do, we know f of x does represent y. So we would just express it as, just because f of x and x can start getting confusing. So we know y is equal to negative 4x plus 6. So first thing we're going to do is step 1, let f of x equal to y. That just simplifies things for us, okay? Next step, we're going to say, we're going to interchange. So step 2, interchange x and y. And when I say interchange, I just mean switch, okay? So where I see y, I'm going to replace that and say it's x, negative 4y plus 6. I just interchange the x and y values. From there, we're going to step 3, isolate for y, meaning when we say isolate for y, we get y by itself. Now, anytime I see y being negative, it's easier for me to take that negative over here and bring the x over here. So this means that 4y is going to equal to negative x plus 6 because I need y by itself. So right now I'm not, right now, y is not by itself. We have that coefficient of 4 up front. And if you recall, to get rid of that 4, we'd have to divide each of our terms by that coefficient. So this would be y is equal to negative 1 over 4x plus, well, we can simplify 6 over 4, which would be 3 over 2. And not done yet. We still have to bring back inverse notation. So step 4, we would say, bring back proper notation for inverse, which is f inverse of x. So therefore, f inverse of x is equal to negative 1 over 4x plus 3 over 2. Now, given the inverse, as you can tell, it's also a linear function. So therefore, we know, we can say, therefore, the inverse of x is a function. Okay, we're going to follow the exact same steps with b, and we're going to state whether the inverse is a function. So first things first, we're going to let f, in this case, g at x equal to y. So y is equal to 1/3 x plus 1 all squared minus 3. Right? That's step 1. Step 2 is interchange x and y, meaning what is y becomes x, what's x becomes y. Okay? And then we solve and isolate for y. So first things first, we're going to bring over that negative 3. So that becomes x plus 3 is equal to 1/3 y plus 1 all squared. Again, we can't get to y until we get rid of everything else around it. So 1/3 times y plus 3. Well, if I wanted to bring that over to the other side, I would multiply this whole side by 3. So that would become 3 times x plus 3 is equal to y plus 1 all squared. All right, so I still can't get y because of that square, that exponent of 2. So if you recall, to get rid of a square, you take the square root. Now, when you take the square root of something, it could either be positive or negative. So we're going to have to say plus or minus 3x plus 3 is equal to y plus 1. Okay, we're still not done. We still need to get rid of that plus 1. So I'm going to bring that over. Remember, when you take it from one side of the equation to the other, this is going to be negative 1 plus or minus 3x plus 3 is equal to y, or y is equal to negative 1 plus or minus 3 bracket x plus 3. Okay, and don't forget, last and final step, and that's very critical, to bring back proper notation. So it's going to be f inverse of x. Well, by mistake put f. Our original function was g at x, so we're going to say g inverse of x is equal to negative 1 plus or minus 3x plus 3. Now, is the inverse a function? Now, we can quickly test it because we know if we substitute one value for x, if there is only one y, then we know that the inverse is a function. So let's see. I'm going to just use 0 because 0 is a really good number to use. So we're going to say if we take the inverse of g at, 0, and I left it as x. Let's change that. Okay, what happens? Do I have one unique value for y? Always following BEDMAS is 0 equal to negative 1 plus or minus 0 plus 3, which is 3. 3 times 3, which is 9, is equal to negative 1 plus or minus square root of 9, which is 3. So we can already tell that when x is 0, y is equal to negative 1 minus 3, which is negative 4, or when x is 0, negative 1 plus 3, which is 2. So therefore, the inverse is not a function, because for the value of x being 0, there is 2 values for y. So each value in the domain does not have a unique value in the range. Okay, moving on. We have given the function f at x is equal to 2 over 3 times x minus 5, evaluate the following. So we remember when we're looking at functions, in this case, f at 2, that means when x is 2, I want to know what the corresponding y value is. So we would substitute input is 2. We want to know what the output is. So 2 over 3, 2 minus 5, always following BEDMAS. 2 minus 5, which is negative 3, which is negative 6 over 3, which is negative 2. Okay, so when the input is 2, the output is negative 2. Or we can say 2 and negative 2. Okay, looking at B, we're asked to find f inverse at negative 2. So in order to do that, we need to have the inverse function. So in order to do that, we're going to use our algebraic skills to take f at x equals 2 over 3x minus 5 and determine the inverse using the proper steps. So let's start with expressing let f at x equal to y. So we're going to say y is equal to 2 over 3x minus 5. That's step 1. Step 2, interchange your x and your y value. So x is equal to 2 over 3 y minus 5. We want y all by itself, so we isolate for y. So we're going to start with bringing that 3 over to the other side, which means we take 3 times x is equal to 2 y minus 5. We need to get rid of that 2, so we're going to divide this side by 2. What I do to one side, I do to the other. So we have 3x over 2 is equal to y minus 5. We still need y by itself, so we're going to bring that minus 5 over to the other side of the equation. Don't forget to change the operation. So it becomes 3x over 2 plus 5 is equal to the y. And then lastly, make sure to bring back proper notation. So we can say, therefore, f inverse of x is equal to 3 over 2 x plus 5. Okay, so now it's easy to determine f inverse at -2 is equal to 3 over 2 times -2 plus 5. So where we see x, replace with -2. So f at inverse at -2 is going to equal to -6 divided by 2 plus 5. F -2 is equal to -6 divided by 2 is -3. -3 plus 5, which is +2. So in this case, when x is -2, y is 2. And if you notice in A, in the original function, when x was 2, y was -2. So we easily could have determined, we know it's the reverse. So naturally, in the inverse, when x is -2, which in the original function, that was your y, x is your original function, x was 2. In the inverse, it would be the y value being 2. Okay, so we're going to use that in C, now that we have the inverse function, to figure out f inverse at 6. So let's start with the original function, where we see x, we can replace it with 6. So 3 over 2 times 6 plus 5. Inverse at 6, 3 times 6 times 3 is 18. Divide that by 2 plus 5. 9 plus 5, which is 14. Okay, last but not least, we have given f at x is equal to k times 2 plus x, find the value of k if we know f at inverse at -2 is equal to -3. So if we know in the inverse when x is -2, y is -3, in the original function, so this is in the inverse, in the original function, that means those, remember, coordinates were interchanged. So we can say the original then, x was -3 and y is -2. You can interchange. Because remember, the inverse is just the reverse of my original. So therefore, we can use that information to help us solve for k. So we can say f at x is equal to k 2 plus x. Then we know when x is -3, y is -2. So I'm going to substitute where I see x -3, and therefore I know that's going to equal to -2. So that'll help us solve for k. So 2 plus -3, which we know is -1. We need k by itself. We're going to divide this side by -1 to get rid of that. Divide that by -1. Those cancel out. -2 divided by -1 is simply 2 is equal to k. So therefore, the value of k is